record. So last class we found that 1 over x was equal to the summation n equals 0 to infinity of x minus 1 to the n times negative 1 to the n, right? So we did that last class, and we found that the interval of convergence for that, and actually, let me move this up a little bit. We found the interval of convergence for it was 0, or I said it was 0 less than x less than 2. So there's a couple other series that are kind of like, you could work through it to find this Taylor or Maclaurin representation of the series, but they're kind of common series that we use. Okay, so one is 1 over x. One is a series 1 over 1 plus x. And so you could go through and find this, in this case, the Maclaurin series for it. If you went through and did all of that, you would get the summation n equals 0 to infinity of negative 1 to the n x to the n. And this converges for negative 1 less than x less than 1. I have, 1, 2, 3, 4, 5, 6, 7, 8. I have 9 kind of common series that we're going to write down. And the reason we're going to write them down is because then we're going to be using these 9 common series for kind of the rest of the problems. If it was on a test, right, I would give you what these series are, unless I'm explicitly asking you to show me that, go through the process of the Taylor or the Maclaurin series. But otherwise, these 9 series we're just allowed to use. So it's kind of like I'm giving you what they are. We could go through and find all these, but we're not going to. But it's the same process we were doing last class to actually figure out what all these are. We can have the series for the natural log of x. And so the series for the natural log of x actually starts with n equals 2. So it's from n equals 2 to infinity of negative 1 to the n minus 1, x minus 1 to the n, all over n. And it converges between 0 less than x less than or equal to 2. So it doesn't start with n equals 0, right? Which is good because n equals 0 would make the stuff on the other side of the summation here, it would make this part undefined, so we can't have it start at n equals 0. And it also doesn't start at n equals 1, and part of that has to do with the way that this series is generally derived. So it's found by actually integrating another series, and so that's why it's kind of starting at n equals 2. The series e to the x is the summation n equals 0 to infinity of x to the n over n factorial. And that's from minus infinity less than x less than infinity. So e to the x is always equal to that series no matter what. Just like the sine of x is equal to the summation n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. The radius of convergence, or the interval of convergence there is also minus infinity to infinity. We have the cosine of x. So summation n equals 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial. So minus infinity less than x less than infinity. And remember last class I think we did the cosine of like 5x, or we did I think we did 5 cosine of 2x or something like that. So it would be the same similar process to get just the cosine of x all by itself. And it kind of looks familiar to like some of the stuff we did the other day, right? When we did stuff the other day, there was a 2n factorial, there was an x to the 2n. We had some other stuff going on as well. Obviously, to keep writing the remaining 3, I have to go to the next page. So I'm assuming you guys are probably still maybe writing. So I'll give you another minute or 2, and then I'll make sure that we're all ready to go to the next page. So you don't have to memorize these. On the test, I would give you any of these. In general, right, if you were doing something, you would probably look one of these up. It's not like I have these series committed to memory. If I need to use one of them, I look them up. So it's not something you have to memorize, but it's kind of nice that we have all these different functions and we can find series representations for them. And again, the reason why it's really helpful to be able to find series representations is because then I can integrate the series. And so if I integrate the series, then I can, so in integrating the series, I can integrate term by term, just the polynomial, rather than the actual function, which a lot of the functions we can't integrate by hand. So that's what's kind of nice about it. So does anybody need more time to copy what I have up there? No? Okay. So we also have the inverse tangent of x, and that series is the summation n equals 0 to infinity of -1 to the n, x to the 2n plus 1 divided by 2n plus 1. And the interval for this one is -1 less than or equal to x less than or equal to 1. And we have the inverse sine of x, which is the summation n equals 0 to infinity of 2n factorial x to the 2n plus 1 divided by 2 to the n factorial squared times 2n plus 1. And that is also from -1 oh, excuse me, to 1. And then finally we have 1 plus x to the k. And so this one's not nice to write in a closed form, but you still can make a series for it. So it is 1 plus kx plus k times k minus 1 over 2 factorial x squared plus k times k minus 1 times k minus 2 over 3 factorial x cubed plus ... right? So the pattern would keep going. So like the next term would be k times k minus 1 times k minus 2 times k minus 3 over 3 factorial x cubed. And this one converges -1. We're going to put a little star next to it, less than x, less than 1. And the star is basically saying it converges at plus or minus 1, so the endpoints, depending on the k value. Right? So for some k's, it would converge, and for some k's, it would not converge. This is actually the binomial series. So this one has a name. This is called the binomial series. binomial series. So the binomial series has to do with Pascal's triangle. So have you guys heard of Pascal's triangle? I was going to say, if you've had me before, you might have seen me do it. Pascal's triangle is pretty cool if you haven't. If you have, okay, so let me show you Pascal's triangle here in a second. We'll take a break from Calc 2 for a minute and talk about Pascal's triangle. But yeah, the binomial series comes from the coefficients are basically the coefficients of like the binomial theorem, which the binomial theorem is related to Pascal's triangle. So, let me know when you guys are, like, I should say, does anybody need me to wait to go to the next page? Okay, so when you're ready, let me know, and then we'll go to the next page. And then we'll talk about Pascal's triangle, since we have time. I feel like Pascal's triangle is one of those things that's pretty cool to see. So, okay. Anybody else need me to wait? No? Okay. So, find the power series 4. Okay. And I'll write the series we're going to use like on the side as we're doing them. You know, if we were in the classroom, I probably would have typed up all of those series for you and put them into a document that then you could have, like, we could have had, you know, sitting on our desk with us. But since we're online, we're kind of tied a little bit to doing it a little different way. So our function f of x is going to be equal to the cosine of the square root of x. So we could do what we did before in terms of finding the Maclaurin series. We could take the derivatives, figure out the pattern. But the thing is now we have some basis to start with. So from the sheet, so I'll kind of put anything that I get off of, or anything I get off of those list of series we did at the beginning. So maybe I really shouldn't put sheet. I'm so used to passing it out on a sheet. So I should do from our starting list. We have that the cosine of x is equal to the summation n equals 0 to infinity of negative 1 to the n x to the 2n over 2n factorial. And so instead, what we're looking for is the cosine of the square root of x, right? So what that means is I am going to go here, and everywhere there's an x instead of an x, how come you can't see my, okay, there we go. Instead of an x, I'm going to put a square root of x, right? So there's only one x showing up here. It's right here. So I'm going to put the square root of x. So this is going to be equal to the summation n equals 0 to infinity, negative 1 to the n, square root of x to the 2n over 2n factorial. So I just took the known series, cosine of x, and since we didn't have an x, we had a square root of x. I replaced x with square root of x. Questions?
Dr. Gorman, just really quick.
Mm-hmm.
What exactly does the square root do?
So it's changing the angle, right? So it's it would be kind of like it's going to change the way that so you know the cosine curve usually just has the period being 2 pi. So it's going to change the way that original cosine curve looks, right? Because you're playing with the angle in there. So basically you're tamping the angle down. So it's taking longer for the angle to get to the values. It's not going to climb quite as fast. So it's going to be like a periodic function, but it's going to look a lot like a cosine curve, but it's going to be, I think probably a little flatter. That's the guess off the top of my head. Does that help?
Yes, thank you so much.
No problem. So x was going between, so the other part of this is that we know that this was converging when 0 was less than x less than 2. So our function here, instead of x being between 0 and 2, it means that the square root of x has to be between 0 and 2, which actually means that x is going to be between 0 and 4, right? So if the square root of x is between 0 and 2, then x itself we can kind of get a little wider range between 0 and 4. So, oh, yeah, where did I pulled the wrong thing. Yes. I just pulled the first one off my series. You're right. It was minus infinity less than x less than infinity. So in this case, it's still going to be minus infinity less than x less than infinity, right? Because it's technically minus infinity less than square root of x less than infinity, which would still just be minus infinity less than x less than infinity. It would help if I pulled the right part off of the sheet. Yeah, I guess technically. I'm not super concerned about that. So yeah, technically, because the square root of x, right, you can't have negatives underneath the square root. So technically we should restrict it to be 0 less than x less than infinity. Yeah. I wasn't going to do the intervals. So I was just worried about us making the series. But yes, you should technically restrict it so you don't get negative values. The other thing I would do here is you can rewrite this part here, square root of x to the 2n. Remember, that's really saying the square root of x squared all to the n power. And so the square root of x squared is just x. So really this is the series n equals 0 to infinity, negative 1 to the n, x to the n, all over 2n factorial. And it's x because square root of x squared just gives us x. Other questions? No. Okay, so let's try another one here. F of x equals x squared sine x. So we know what sine x is, right? So sine x was one of the ones that was given. Sine x is the summation n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. So here, I just have a sine n, right? Or sine x. I just have a sine x, so I can replace this sine x with what that series is. So this is going to be x squared times the series n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And then the thing is I can take that x squared is being multiplied. So it's multiplied times each of the pieces of that sum. So I can take the x squared and pull it inside the summation. So it's going to be the summation n equals 0 to infinity, x squared times negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial, or the summation n equals 0 to infinity, negative 1 to the n. I can put the x's together, so I'd have 2n plus 3 of them, all over 2n plus 1 factorial. Questions? No? Does anybody need me to wait to go to the next page? No? So we've got f of x equals sine x minus x plus x cubed over 3 factorial. So again, we're going to use the sine of x is equal to the summation n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So if I plug that in, we've got here the summation n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. All that, and then we're subtracting off an x, and we're adding an x cubed over 3 factorial. So, unlike the last example, where in the last example I could just multiply the x in, here I have these extra pieces hanging off. So you technically could leave it like that. However, if at all possible, we like to make it into just one summation. We would just kind of like it a little bit cleaner, a little bit more straightforward, neater. So when you have a situation like this, where you have some pieces that you're adding onto your series, it's oftentimes a good idea to write out the first couple terms of your series and see if there's any way you can incorporate these other pieces into it. So if I begin to write out the terms of my series, right? So I'm going to have some terms of my series, then we have minus x plus x cubed over 3 factorial. So let's try to figure out what these are. So we're starting with n equals 0, right? So at n equals 0, we're talking about negative 1 to the 0, x to the 2 times 0 plus 1 over 2 times 0 plus 1 factorial. Plus, the first term would be negative 1 to the first, x to the 2 times 1 plus 1 over 2 times 1 plus 1 factorial. Right, that's the n equals 1 term. The next term would be negative 1 squared, x to the 2 times 2 plus 1 over 2 times 2 plus 1 factorial. That's the n equals 2, and so forth. Right? And if I actually work out what these are, so that n equals 0, negative 1 to the 0 is 1. On the top, I just have x to the first, so we have an x to the first. On the bottom, we have a 1 factorial. The next term turns out to be negative, and then we have an x cubed over 3 factorial. The next term will be positive, and then we have an x to the 5th over 5 factorial. And this is going to continue, right? It's going to alternate positive and negative, and then I still have this minus x plus x cubed over 3 factorial. So x to the first over 1 factorial, that's just x. So really I have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus minus x plus x cubed over 3 factorial. Any questions on anything I did so far? No. Okay, so then if you look at these, right, this is a minus x. It would cancel out with this positive x. This minus x cubed over 3 factorial would cancel this x cubed, positive x cubed over 3 factorial. So really, the only thing I have is this part of the series left. And remember, this came from the n equals 2 term, right? So I basically just have the series, but instead of starting at n equals 0, it's really just going to be start at n equals 2. So n equals 2 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Questions? No. Guys are very questionless today. Should we do a couple more? All right. Does anybody need me to wait before I go to the next page? No. Okay. So what was that? That was C. Yeah. Okay, so D, f of x equals sine squared of x. Excuse me. So, you might be tempted to take the sine series, right? So we have the sine of x is summation n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial, right? So you might be tempted to take that and to actually square that out. However, that is really difficult because remember, this side here is a bunch of things added together, right? So this side here is a whole bunch of terms that are all added together. And think about, and it goes on forever. So you have an infinite number of terms added together. And so if you square that, that's not as easy as just distributing the square in, right? You would have to take this infinite number of terms and multiply it by another polynomial that has an infinite number of terms. You'd have to start like taking the first term times all the things in the second polynomial in the second one, the second term times all the things in the second one. So it's a big mess. So we need to figure out another way. So if you remember way back when we were doing the techniques of integration, we actually could use the half angle or the double angle identities to rewrite sine squared of x. So sine squared of x is actually 1 minus the cosine of 2x all over 2. Does that vaguely sound familiar? All right. So I could break this up a little bit. This is really 1/2 minus 1/2 the cosine of 2x. So all I did remember is there's like a 1 here in front of this cosine of 2x. So since I had multiple pieces on the top but only one thing on the bottom, I could split it. So I've put the 1 over 2 and the minus 1 cosine 2x over 2. And then I just wrote that with the 1/2 in front. And then we know that the cosine of x, that summation is the summation n equals 0 to infinity of -1 to the n, x to the 2n plus 1, x to the 2n, all over 2n factorial. So this is going to be 1/2 minus 1/2 times the summation n equals 0 to infinity, -1 to the n, x to the 2n over 2n factorial. So just like we did in the last one, we are going to look at this series and see if we can figure out kind of what's going on. So we're going to write out some terms just like we did before. So I'm going to have 1/2 minus 1/2 times. Okay, if I plug in 0, we're going to have -1 to the 0, x to the 2 times 0, all over 2 times 0 factorial, plus -1 to the first, x to the 2 times 1, all over 2 times 1 factorial, plus -1 squared, x to the 2 times 2, all over 2 times 2 factorial, plus -1 cubed, x to the 2 times 3, all over 2 times 3 factorial, and so forth. Oh, yeah, it is 2x to the 2n. Thank you. Right. I have here a 2x, so this should be 2x to the 2n. All right. Since you guys probably have to just I'm going to rewrite it correctly. Right. So if you just want to put an X through your notes and rewrite this first part again, and then write what I'm going to do. Yes, thank you. Apparently I'm not on my game here today. So we've got 1/2 minus 1/2. The summation, -1 to the n. Instead of an x, we have a 2x. So 2x to the 2n all over 2n factorial. That is lucky, right, if you didn't write it down. So, yeah. I don't know what my deal is. Actually, I shouldn't say that. I do know what my deal is today. So, you know, while you guys are kind of catching back up with me and writing, I think I've mentioned, right, I have a daughter, and so she's 14 months old, and so she recently has just been getting into everything, and so we kind of like reconfigured our living room and all this stuff and put up baby gates. And so, you know, when we put the baby gates up the other day, my husband put the first one up pretty high. And I was like, this is really high to step over. And he's like, okay, fine. And we lowered it. And so then I'm fine climbing over the baby gates. But apparently yesterday he was having a bad day and he fell over the baby gates twice. So he's like, his back is all like messed up today. So I've been on like baby duty all day long. And then I literally like kind of threw her in the crib for nap time, like 2 minutes before class started. So yeah, so that's kind of been my day so far. So I think that's why I'm kind of a little off. And that's more information than you probably needed to know about my life, but, you know, keeps it kind of interesting, right? Okay. So, back to the problem at hand here, now that I do it correctly. We have 2x to the 2n, right? Because we had a 2x instead of just an x. And so now I'm going to actually write out some of these terms. So I have 1/2 minus 1/2 times, so we have -1, oops, this should be n equals 0 to infinity. So we have -1 to the 0, 2x to the 2 times 0, all over 2 times 0 factorial, plus -1 to the first, 2x to the 2 times 1, all over 2 times 1 factorial, plus we have -1 squared, 2x to the 2 times 2, all over 2 times 2 factorial, plus -1 cubed, 2x to the 2 times 3, all over 2 times 3 factorial, plus ... And so if I begin to work this out, right, we've got 1/2 minus 1/2 times. Okay, so the first one there, everything is to the 0 power on the top. So on the top I have a 1, and on the bottom I have a 0 factorial. Remember, 0 factorial is just 1, so that whole first term is just 1. Then we're going to have, I have -1 to the first, so it's going to be negative. This is going to be 2 squared x squared over 2 factorial. Then we're going to have a plus 2 to the 4th x to the 4th over 4 factorial. Then we're going to have a minus 2 to the 6th x to the 6th over 6 factorial. And we're going to continue that pattern. Yeah, so why is 0 factorial 1? 0 factorial, so there's a couple reasons. So some people tell you, 0 factorial mathematicians define as 1, so things work out. But the factorial, kind of what the factorial represents is it's kind of the number of ways of arranging objects, right? So if we think about 3 factorial, right? So 3 factorial we know is 6. So let's say you were trying to arrange 3 pieces of fruit in a line in front of you. So say an apple, a banana, and a pear, right? The way that you can write an apple, a banana, and a pear, there's 6 different orders you could put it, right? You could put an apple first, banana second, pear third. You could do an apple first, a pear second, the banana third. You could do a banana, then an apple, then a pear, a banana, then a pear, then an apple. Or you could do a pear, then an apple, then a banana, or a pear, a banana, and then an apple, right? So there's 6 different ways you can arrange it. 0 factorial means you have no objects and you're trying to arrange them. Well, there's only one way to do that, by doing nothing, right? I have nothing in front of me to arrange, so there's nothing to do. There's just one way to do that. One way to do nothing. So that's kind of like the other way you can think about why 0 factorial is 1. Does that help? No problem. Okay. So I can take that 1/2 and multiply it through, right? So if I take that 1/2 and multiply it through, I'd have 1/2. 1/2 times this, we said 0 factorial is 1. So that's just a giant 1. So that's going to be minus 1/2. Then we're going to have minus 1/2 times 2 squared x squared over 2 factorial, right? Oops, times negative. Minus 1/2 times 2 to the 4th x to the 4th over 4 factorial. Minus 1/2 times negative 2 to the 6th x to the 6th over 6 factorial. And so forth. So I really end up with 1/2 minus 1/2. In all of these, this 2 would cancel one of these, right? So this 2 cancels one of these. This 2 cancels one of these. So we really have 1/2 minus, and really I should say 1/2 minus 1/2. They cancel each other out, right? So really what I have left is I have 2x squared over 2 factorial minus 2 cubed x to the 4th over 4 factorial plus 2 to the 5th x to the 6th over 6 factorial minus, and we would keep going, right? And I would like to write this in a closed form, right? So, summation, and we're going to figure out where we're going from. So we're going to start someplace but go to infinity. But we have to figure out where we're going to start here. So the bottom, we didn't really change the bottoms from what the original bottom was, right? So the bottoms here was just 2n factorial. So that's, we just still have 2n factorial. And we want our first bottom to be a 2. So the way to get a 2 out of this, we would want n to be 1. So that means we're going to start with n equals 1. And then we still have x to the 2n. And then we have 2 to a power. But the 2 is always 1 less than the x. So it's going to be 2n minus 1. And I didn't really leave myself enough room at the beginning to put. But we also have negative 1 to a power. We want the first one here to turn out to be positive, right? If you're looking, I have a positive, then a negative, then a positive, then a negative. So I want the first one to be positive. So when I plug n in, I want this to be positive. So if I just put an n, it would be negative. So this needs to end up being an n plus 1. Because now when I put the 1 in, 1 plus 1 is 2. And this would turn out to be positive. So in terms of trying to figure out your power on the negative 1, I always start with negative 1 to the n. And then I see, would that work? Or do I need to add another 1 to it? So in this case, you need to add another 1 to it. So that is the nice little closed form for that. Questions? No? Okay, so I have one more, which uses a completely different trick. Does anybody need me to wait till we go to the next page? Yeah. Okay. I think this is, E. F of x equals 1 over 1 minus x cubed. Okay, so I have nothing that exactly looks like this, right? I have, from that list of original those like 9 power functions I gave you at the beginning of class, there's this one, which is the closest to what we have going on. We had 1 over 1 plus x was equal to the summation n equals 0 to infinity of negative 1 to the n, x to the n. And so you might go, well, it's kind of close, right? Like, there's kind of 2 things that are different. One is that you have a minus x instead of a plus x. That's easy enough for us to fix. The other thing is that you have to cube it. The problem, again, is kind of like the problem we had, I think it was like 2 or 3 examples ago when we had the sine squared. I do not want to cube this infinite series here. I don't want to do it, right? Like, I can't really cube it. So I need to figure out another way. So the trick is actually to actually take the derivative of this function. So if we think about, if I start with 1 over 1 minus x, so if I started with the function, we'll call it g of x as 1 over 1 minus x, right? And that's really 1 minus x to the negative 1. G prime of x would be what? Okay, so the negative would come down. I'd have negative 1 minus x, and then what power would that be to? Right, power comes down in front, and then you, remember, subtract 1 from the power. So it would be to the negative 2. And then you have to multiply times the derivative of the stuff inside. So the derivative of the stuff inside is negative 1. So really this is 1 minus x to the negative 2 power. So that's kind of nice. It's getting me closer to the power we need. We need a negative 3. So if I took the derivative again, I took the second derivative, we would have negative 2, 1 minus x to the negative 3 power times the derivative of the stuff inside. The derivative of the stuff inside is negative 1. So this would give me 2 times 1 minus x to the negative 3, or 2 over 1 minus x cubed. So it's pretty close to what I started with, right? What's the only difference between what we have, the second derivative, and what we started with? Yeah, the 2, right? So we could think of f of x is really 1/2 times g double prime of x. Does that make sense so far? Yes? No? Questions? Yes. Okay. G of x, right? I can use this to rewrite G of x, right? The only difference between this and G of x is that we have a minus x, where here it's a plus x. So G of x we could write as the summation n equals 0 to infinity of negative 1 to the n times negative x to the n, right? Because instead of a positive x, we have a negative x. And you could put those together, right? So this would be the summation n equals 0 to infinity of negative 1 times negative x, all to the n power, or the summation n equals 0 to infinity of just x to the n. Okay, so you might go, okay, well, how's that going to help me? Well, that's helping us because we know that the function we're looking for, f of x, is going to be 1/2 the second derivative of that summation. So 1/2 the summation n equals 0 to infinity, x to the n. We're going to take the second derivative of that. Okay, so to be able to take a second derivative, you first got to take the first derivative. So the first derivative of n equals 0 to infinity of x to the n. So we're just taking the derivative of all the pieces inside. So what's the derivative of x to the n? What would that be? Think of it like it's an x cubed, but instead of a 3, we have an n. Yeah, so it would be n x to the n minus 1. Now, the very first piece, when you plug in n equals 0, right? N equals 0 is just x to the 0, which is just 1. Remember, the derivative of a constant is 0. So the first piece, when you take the derivative of the series, goes away. So the derivative actually starts at n equals 1. And now we want to take the derivative of that. So n equals 1 to infinity of n x to the n minus 1. So same thing, it's just the power rule again. Same thing, that first piece is going to go away. So this is going to be n equals 2 to infinity, n times n minus 1, x to the n minus 2. So our answer here is going to be 1/2 the summation n equals 2 to infinity of n times n minus 1, x to the n minus 2. And then you could bring the 1/2 inside if you wanted. So the summation n equals 2 to infinity of 1/2 n times n minus 1, x to the n minus 2. Questions? No? Okay, so that's the end of what we were going to cover. So that kind of finishes series and sequences for us. Can I explain the blue part again? Sure. So the blue part comes from, I'm comparing the 1 over 1 minus x with the pink part up here, the 1 over 1 plus x. So the only difference between these is I have a minus x rather than a plus x. So when I copy this series down, rather than putting a positive x here, I put in the negative x. So does that first blue step make sense? Let's just start with that. Okay. Now I have both things raised to the n power. So what that means is I can kind of like, in some ways, like factor the n power out because they're being multiplied times each other. And so that's all I did was I thought about bringing the n to the outside here. Because if you were to kind of like redistribute this, right, you would get -1 to the n, negative x to the n. So I'm kind of doing it the other way. I pulled the n power up to the top. So now I have -1 times negative x. So does that make sense? It's okay if it doesn't make sense. I just need to know then that it doesn't make sense. I'm not frozen too, guys, right? Like, that happened in one of my other classes. I was talking, but then I was frozen. So can someone let me know that, like, you can still hear me and stuff? Okay. Okay. So then what I did was basically I pulled this n out, and then I had -1 times negative x gives me just positive x. And so then inside here I end up with a positive x, so it's positive x raised to the nth power. Does that help? Any other questions before I go off of this problem? Yeah, so where the 1/2 comes from is because I'm comparing this, oops, I flipped it with my hand. I'm comparing this function here, the one we were given, the 1 over 1 minus x cubed, with this. So the difference between, so I have 1 over 1 minus x cubed, right? That's what I want to get. And I want to get there from this function. So the way to take this function and get here is to get rid of the 2. So to get rid of the 2, I would need to multiply by 1/2 here. So if I multiply this function by 1/2, I'll get what I'm looking for. So that's why I have 1/2 times g double prime. Does that help explain it? No problem. Other questions? No. Okay. So then, what I want to do is I want to talk about the test for a couple minutes, show you guys that. So let me stop sharing this. I can put it back up if anybody needs it after we talk about the test here. Okay, if you go to Canvas, right, and you go down here to test reviews, I have the review for the test up for the third test. So I have a couple things. Oh, I should change these so these, I don't know why both of these. I have to fix this because I see it's not exactly right. So it should be the review sheet. It should be answers to the review sheet. Then it should be, I put up extra practice on series. So if you need some more practice on series, and then the answers to the extra practice. So I don't know what happened. Canvas keeps being weird for me here. But anyway, let's look at the review sheet here for a second. So did that pop up so you guys can see the review sheet? Yes. Okay, perfect. So basically, most of the test is going to be just determine if a sequence or series converges or diverges, right? So we did a very tiny little bit of sequences at the beginning. Then we went into geometric and telescoping series. Those are the only ones you can find the sum of. And then determine whether stuff converges or diverges. We did stuff with determining whether it converges absolutely or conditionally. We did the radius and interval of convergence for power series. Then we did Taylor-Maclaurin series. That's what we did last class. And then we did finding the power series. And kind of I put here, like, if you can do the homework problems, you'll have no problem with the test problems. And then I put here's some, determine if the following converge or diverge. Here's one, determine whether the sequence is convergent. And then find the sum. So if I'm asking you to find the sum, these are either going to be a telescoping series or a geometric series, because those are the only ones we can find the sum of. Here's a couple other examples. So these are things that you could kind of look at. If I were you, I would try some of these before next class, so that way then, if you have questions, I can help you out and go over them. So the test, as I said before, is 1 week from today. So next Thursday on the 22nd, and, Tuesday's class, so on the 20th, will just be about answering questions and anything you guys have for series, and sequences for the test. So, questions, anything I can answer for anybody? No? Okay. Then I will see you all on Tuesday. We'll end there for the day. I knew we'd get done a little bit early today, just because we didn't have that much to finish up.